Have you ever paused to look up at the night sky and just felt profoundly small? Or maybe wondered, on a quiet evening, how something as incredibly complex as a human being could possibly emerge from?
Yeah.
Well, just ordinary stuff.
Yeah, absolutely.
And then perhaps the biggest question of all, in this vast, seemingly indifferent cosmos, do you, or any of us, actually matter?
Those really are the fundamental questions, aren't they? The ones humanity has grappled with forever. What is the universe really made of, like at its deepest level?
Yeah.
How did life arise from just chemistry?
Right.
How does consciousness, this feeling of being me, emerge from a physical brain? And maybe the toughest one, if the universe doesn't have some preset purpose, where does our sense of meaning even come from?
Exactly. And our mission today is to take a stack of fascinating material that dives deep into these very questions specifically, drawing heavily on excerpts from Sean Carroll's book, The Big Picture, on the origins of life, meaning, and the universe itself.
Yeah, it's a great source for this. Our goal is basically to take you on a guided tour through these massive ideas. We want to help you understand the universe, life, consciousness, and even meaning, as seen through a modern scientific lens and, well, a particular philosophical framework the source uses to tie it all together.
Now, this is complex territory, no doubt about it. We're covering pretty much everything. So we're going to take our time with this. We'll break down the really big ideas step by step, try to explain things clearly.
Definitely.
Make sure you can grasp the essential points without feeling completely lost. Think of this as a slower, more careful exploration.
And central to this whole exploration is that framework the source calls poetic naturalism. It sounds a bit unexpected together, doesn't it? Poetic and naturalism.
It really does, like mixing hard science with poetry. Okay, let's unpack what that actually means.
It actually captures the two core ideas really beautifully, I think. First, you've got naturalism. This is basically the scientific view that there's fundamentally just one world, the natural world. It operates according to impersonal, discoverable laws. There's no separate realm of, magic or spirits or outside interventions that can affect the world in ways that science couldn't, in principle, detect.
Right.
Everything that happens is ultimately a result of the workings of this single natural reality.
So, one reality, governed by understandable rules, no hidden strings being pulled from, outside the system.
Precisely. And the poetic part is crucial, too. It reminds us that even though there's only one underlying reality described by fundamental physics, there are many valid, useful, and even beautiful ways to talk about this reality.
Oh, okay.
We use different vocabularies, different stories, you could say, depending on what level of complexity we're looking at.
Like describing a jumble of atoms versus describing a ship? Is that the kind of thing?
That's a perfect example the source uses. A ship is undeniably made of atoms, right? Following fundamental laws. But trying to talk about the ship's journey across the ocean or its history or its design by listing every single atom and its state, well, that would be impossible.
And kind of pointless.
Totally pointless, and it would completely miss the point. Talking about the ship as a ship, its buoyancy, its speed, who built it, that's a completely valid and useful way to describe that particular collection of atoms.
And this isn't just simplification for convenience. These higher level descriptions capture something real about the world.
Exactly. They reveal true, important features of reality that might be totally hidden if you only looked at the deepest microscopic level. Think about the air in this room.
Okay.
At the most basic level, it's just molecules bouncing around following quantum rules. But to understand whether or how a plane flies, you need the concept of fluid, something with properties like density and pressure.
Right. You wouldn't talk about individual air molecules when predicting a storm.
You couldn't. Talking about air as a fluid reveals patterns and behaviors that are real and absolutely essential for understanding the world at that scale.
Okay, so poetic naturalism. One fundamental natural reality, but multiple ways of talking about it, multiple lenses depending on the level of organization. And these emergent descriptions, these stories, are just as real and useful as the fundamental ones.
That's the core idea. And our deep dive today will kind of follow that structure. We'll explore the universe's fundamental reality described by physics, then how complex things like life and consciousness emerge through these patterns at higher levels.
Okay.
And finally, what this whole perspective tells us about how we find meaning and build morality in a world governed by these impersonal laws.
And that sounds like quite a journey. Let's start right at the bottom then, the fundamental canvas of reality itself. Our first section is about the basic stuff and the physics that describe it.
Right. So poetic naturalism suggests that the deepest level of reality, the most fundamental way of talking about it, might be very sparse. The source material talks about a sparse fundamental ontology.
Sparse ontology,
Meaning, the bedrock could be described by a very limited set of basic entities, like maybe just quantum fields. The things we usually think of as solid particles, electrons, photons, quarks, could just be manifestations, like excitations or vibrations of these underlying fields.
so not tiny hard balls zipping around, but more like ripples in some fundamental cosmic ocean.
That's one way to visualize it, yeah. A very minimalist description right at the bottom. But then, from that sparse foundation, we build up to the richer emergent ontologies, the concepts we create and find useful, like ships, people, ecosystems, economies. These are the ways we talk about reality at higher levels of organization.
And you mentioned the Ship of Theseus puzzle earlier
Yeah.
that fits in here.
Yes, it's a classic way to show how these emergent concepts work. If you replace every single plank of wooden ship over many years, is it still the same ship at the end?
Right, the philosophical headache.
Exactly. And the source points out that the question itself only makes sense because ship is a concept we invented for our convenience. Whether it's the same ship isn't some objective fact hidden in the fundamental quantum state of the atoms. It's a judgment call we make based on our useful, higher-level way of talking about that collection of planks and nails.
Because tracking the atoms would be impossible and wouldn't tell us what we mean by ship anyway.
Precisely. And the air example, again, shows why these richer descriptions aren't just convenient, they're necessary.
Okay.
We could try to describe the air in a room by listing the state of every single molecule, trillions upon trillions of them. But that's utterly impractical. And more importantly, it wouldn't tell you anything useful about how air behaves as a whole, how it flows, its temperature, its pressure. Those are emergent properties.
Properties that only become visible when you step back and look at the system from a higher level, using concepts like density or fluid dynamics.
Exactly. Those concepts capture real patterns and allow us to make predictions and understand the world in ways the microscopic description alone wouldn't.
So these emergent ways of talking aren't less real, they're just different stories.
Right?
Different, valid, useful ways to describe the same single underlying reality.
That's precisely the idea. The source distinguishes different kinds of these stories or ways of talking.
Yeah.
You've got the fundamental description, like quantum fields. Then you have emergent or effective descriptions, which is what most of science deals with: chemistry, biology, psychology. And crucially, you also have ways of talking about values, morality, purpose, meaning.
Okay. So science mostly handles the first two.
Science excels at the fundamental and the emergent descriptions of what is. Values are a different kind of story. But sticking with the what is for now, how does physics describe how the universe changes over time? The source mentions a big shift in thinking happened historically.
Right, from things having purposes to just laws.
Yeah, a profound shift. Think back to Aristotle. He thought physics was teleological. That means objects and processes had inherent purposes or goals, a telos, built right into them.
Like an acorn's purpose is to become an oak tree.
Exactly. He even described 4 causes for everything. The material cause, what it's made of; the formal cause, its structure or form; the efficient cause, what directly made it happen; and the final cause, its purpose or end goal.
But that's not how we think about physics now.
Not at all. Thinkers like Galileo, and especially Newton, shifted the focus entirely. They looked for impersonal laws and patterns like the conservation of momentum. Objects move not because they want to reach some goal, but because they follow predictable mathematical rules. Force equals mass times acceleration, that kind of thing.
It sounds very mechanical, almost deterministic, like the universe is just a giant clockwork machine. If you knew the position and momentum of every particle right now, you could perfectly predict the future.
That's the classical idea, captured by Laplace's demon, a hypothetical superintelligence that could know everything about the present and calculate all of the past and future. And yes, the fundamental laws in classical physics are deterministic in that sense. Given the initial conditions, the future unfolds in only one possible way.
But modern physics threw a spanner in those clockwork works,
yeah.
right? Things got a lot weirder at the really small scale.
Much, much weirder. Classical mechanics basically broke down when trying to explain atoms and light. It was replaced by quantum mechanics for describing reality at that fundamental level.
Okay, quantum mechanics. Uh-oh.
Yeah, deep breath. In QM, you don't have little particles with definite positions moving along definite paths. Instead, you describe systems using a quantum state, often represented mathematically by something called a wave function.
The source uses the hydrogen atom example, right?
Yeah.
Why doesn't the electron just spiral into the nucleus like classical physics says it should?
Exactly. A negatively charged electron orbiting a positive nucleus should radiate energy and collapse inwards almost instantly, according to classical electromagnetism. But atoms are stable.
Thank goodness.
Indeed. QM describes the electron not as a tiny ball orbiting, but as a wave function, kind of smeared out in a probability cloud around the nucleus. And this wave function evolves smoothly and deterministically according to the Schrödinger equation, as long as you don't look.
There's the catch. The looking part. The measurement problem.
That's the mystery, yes. When you observe or measure a quantum system, like trying to find exactly where that electron is, the outcome seems to be probabilistic, random. It's as if the wave function suddenly collapses from a spread out wave of possibilities into one definite state.
So even though QM is incredibly accurate, it makes predictions that are verified to astonishing precision. Physicists don't actually fully agree on what's really going on when we make a measurement.
That's basically correct. There are different interpretations. Many worlds, Copenhagen, pilot waves, and others trying to make sense of this measurement process and what the wave function truly represents. It's one of the biggest unresolved debates in fundamental physics, despite the theory's unbelievable empirical success.
Wow. Okay. But leaving the measurement weirdness aside for a second, you said the underlying equations, like Schrödinger's, are deterministic when this system is left alone.
Yes, the evolution of the wave function itself is deterministic. And what's also fascinating is that these fundamental laws, both classical and quantum, before you get to the measurement issue, are generally time-symmetric.
Time-symmetric, meaning they work the same forwards and backwards in time.
Exactly. The equations don't inherently distinguish between the past and the future. If you recorded a video of, say, two particles colliding according to the fundamental laws and ran the video backwards, it would still look like a perfectly valid physical process.
But hang on. That can't be right for us. Our experience is totally not time-symmetric. Eggs break, they don't unbreak. Cream mixes into coffee, it doesn't spontaneously unmix. We remember yesterday, not tomorrow. Why is there such a clear arrow of time in our everyday world if the fundamental laws don't care about direction?
Ah, yes, the arrow of time. This is a huge point, and the explanation is incredibly profound. It's tied to the concept of entropy.
Entropy, usually explained as disorder, right?
Sort of. It's maybe better thought of as a measure of how spread out or useless energy is. Think of a steam engine. It uses concentrated heat, low entropy, to do work, but inevitably releases waste heat, high entropy, that's too spread out to be useful. Entropy is a measure of that uselessness, or you could say disorderliness.
Yeah.
And the crucial rule here is the second law of thermodynamics.
The one that says entropy always increases.
In a closed system, yes. The total entropy never decreases, it only stays the same, or much more likely, increases over time. Things naturally tend towards states with higher entropy, more disorder, more spread out energy. Like my desk, it naturally gets messier unless I put energy into tidying it.
That's the perfect analogy. Tidying your desk, decreasing its local entropy, requires effort. You expend energy, radiate body heat, increasing the total entropy of the room and the wider environment. The overall entropy always goes up. The universe as a whole tends towards increasing disorder over cosmic timescales.
Okay, so things tend towards disorder. But if that's the natural endpoint, maximum disorder, why didn't the universe start out that way? Where did the initial order come from, the low entropy state that allows things to get messier?
And that is the absolute key insight according to the source. The arrow of time we experience, the reason things happen in one direction, isn't baked into the fundamental laws themselves. It comes from a very, very specific initial condition of our observable universe.
An initial condition, like how it started. Exactly. There's something physicists call the past hypothesis. It's the assumption strongly supported by cosmological observations that the early universe, right after the Big Bang, was in a state of incredibly low entropy, exceptionally ordered, incredibly smooth, very unlike the clumpy, complex universe we see today.
So the universe started off incredibly neat and tidy, and the arrow of time is just the story of it getting progressively messier ever since.
That's the essence of it. Because it started in such a special low entropy state, there was room for entropy to increase. This increase in entropy drives all the irreversible processes we see: stars burning, life evolving, eggs breaking. Time's arrow isn't fundamental to the laws. It's what the source calls ekinological. It arises from this incredibly special, ordered starting point way back in the past.
Wow. Okay.
Yeah.
That's a really big idea. The reason time flows is because of the beginning. Okay, let's zoom back in a bit. What about the physics that governs our everyday lives? Not the Big Bang, but, tables being solid, gravity pulling us down, chemistry working.
Right. For that, the source introduces what it calls the core theory. This isn't a single unified equation, but rather the well-established set of quantum field theories that reliably describes the particles and forces relevant to everything we encounter in daily life, up to the energies we can currently probe well.
So what's in this core theory?
It includes the familiar stuff: electrons, quarks, which make up protons and neutrons inside atomic nuclei, photons, particles of light, the strong and weak nuclear forces, electromagnetism, gravity, as described by general relativity in this context, and the Higgs boson, which gives particles mass.
And it classifies particles, right? Fermions and bosons.
Yes. You have fermions, which are the matter particles, electrons, quarks. They obey the Pauli exclusion principle, meaning no two identical fermions can be in the same quantum state, which is basically why matter takes up space and feels solid. Then you have bosons, which are the force carriers. Photons carry electromagnetism, gluons carry the strong force, W and Z bosons carry the weak force, and the Higgs boson is also a boson.
Okay. And the source makes what sounds like a huge, almost, well, the word used is audacious claim about this core theory.
It does. The claim is the laws of physics underlying everyday life are completely known.
Completely known. That sounds
Yeah.
incredibly bold. What does that actually mean? And maybe more importantly, what doesn't it mean?
That's the crucial part. It absolutely does not mean we know all of physics. There could be entirely new physics at much higher energies, like those near the Big Bang, or inside black holes, or maybe involving dark matter or dark energy, or extra dimensions, things we don't understand yet.
Right. So it's not theory of everything.
Definitely not. And just as importantly, it emphatically does not mean we know how everything works at the everyday level using these laws. We don't have complete fundamental theories derived purely from the core theory for incredibly complex emergent phenomena like, say, consciousness or turbulent weather patterns or the stock market or how a specific protein folds.
Okay. So we know the basic rules and the players down here at the scale is relevant to us, but figuring out how those rules lead to all the complex structures and behaviors we see, that's where all the other sciences, like chemistry, biology, geology, psychology, come in.
Precisely. The claim is just that within the domain of energies and phenomena relevant to everyday life, chemistry, biology, technology, we know the fundamental laws governing the constituents. We don't expect some new fundamental force or particle to pop up and suddenly change how chemical reactions work or how transistors operate.
And the evidence for this claim comes from experiments.
Decades and decades of incredibly precise experiments, especially at particle colliders. For instance, the source mentions the Large Electron-Positron Collider, LEP, at CERN. They smashed electrons and positrons together with very high, very precisely controlled energies. They were specifically looking for any signs of new particles or forces predicted by theories that go beyond this core theory, particles that should have shown up within that energy range. And they found nothing unexpected. The results perfectly matched the predictions of the core theory, specifically the standard model part of it. That gives physicists enormous confidence that, at least up to those energies, we've got the fundamental pieces right for the world we live in.
What about gravity? It always feels like the odd one out. It's so weak at the particle level, and we haven't definitively found its quantum particle, the graviton. How does it fit in the core theory?
Gravity is different. It's much weaker than the other forces at small scales, but it's long range, and crucially, it's always attractive. It accumulates. More mass always means more gravity.
Which is why we feel the Earth's gravity, even though the force between individual atoms is tiny.
Exactly. We feel the combined pull of every atom in the Earth. While integrating gravity fully with quantum mechanics, creating a quantum theory of gravity is still a major challenge for theoretical physics, especially at extreme scales like black holes or the Big Bang. Einstein's theory of general relativity works perfectly well for describing gravity in the realm of everyday life, from falling apples to orbiting planets. And it's included as the description of gravity within the scope of the core theory. We don't need quantum gravity to understand why we stick to the floor.
Okay, so the fundamental stage is set. Known physics operating within the core theory, plus this special low entropy beginning that gives us the arrow of time. What of the very existence of the universe itself? Does science say anything about why there's something rather than nothing?
That's pushing the boundaries of what science can currently address, or maybe even ever address in the way people often want. Science can suggest that, based on the known laws, a universe like ours could exist all by itself, without needing any external creator or sustainer to get it started or keep it going.
How so?
For example, the fundamental equations of quantum cosmology, like the Wheeler-DeWitt equation, a sort of Schrödinger equation for the whole universe, have solutions that describe a universe that could exist eternally, perhaps undergoing cycles, or even potentially tunneling into existence from literally nothing, depending on the specific model. The point is, the laws themselves might allow for self-contained existence.
But, as the source points out, saying it could exist according to the laws isn't quite the same as explaining why it exists, or why these laws instead of some others. That feels more like a philosophical question.
Exactly. Science describes the what and the how based on observation and testable laws. The ultimate why of existence itself might lie beyond its scope, which naturally leads us to the next big step. Given this fundamental stage, this physics, how do we get all the incredible complexity we see around us? Especially something as remarkable as life.
All right, section 2. The emergence of complexity, life, and evolution. This seems like a puzzle. If the universe's fundamental tendency is towards increasing entropy, increasing disorder, according to the second law, how do you get incredibly ordered things like, well, us? Or even just a single cell?
That's a really important question, and it highlights something crucial we touched on earlier. The second law of thermodynamics, the tendency towards increasing disorder, strictly applies to isolated systems that don't exchange energy or matter with their surroundings.
But life isn't isolated.
Not at all. Life, and indeed many complex systems, are fundamentally open systems. They constantly interact with their environment, taking things in and putting things out.
Like the refrigerator analogy again. It creates order inside, coldness, by actively pumping heat disorder out into the kitchen.
Perfect analogy. Order can increase locally. Entropy can decrease in a specific spot, like inside the fridge or inside a living cell building complex molecules, as long as this local ordering process generates even more entropy in the wider environment. The total entropy of the larger isolated system, like the universe as a whole, or the fridge plus the kitchen plus the power plant, always goes up.
So life creates these amazing pockets of order, but it does so by taking in useful energy and spitting out waste heat, effectively increasing the overall disorder of the universe even faster than if it weren't there.
That's exactly the idea. Life is incredibly effective at finding sources of useful low-entropy energy, like sunlight or chemical gradients, and degrading it into spread-out high-entropy heat, using the energy flow to maintain its own complex structure and perform functions.
And this kind of organization, this complexity, it can just happen spontaneously, without needing a designer or a blueprint.
Yes, surprisingly complex patterns and large-scale order can emerge spontaneously from simple local interactions following basic rules. The source mentions the Schelling segregation model as a simple example.
What's that?
It's a computer model where you have, say, two types of agents, like dots of different colors on a grid. Each agent just follows one simple rule. If less than, say, half of my neighbors are like me, I'm unhappy and I'll move to a random empty spot.
Okay, seems simple enough.
But what happens when you run the simulation is that even if everyone would be perfectly happy in a mixed neighborhood, these simple local preferences inevitably lead to large-scale segregation. Distinct neighborhoods of mostly one color or the other emerge across the whole grid purely from those local interactions.
Yeah.
No central planner intended it.
Wow. So local rules can create global patterns.
Exactly. And this happens with molecules, too. Simple intermolecular forces cause oil and water to spontaneously separate into distinct layers. Even more relevant for life, lipid molecules, fatty molecules in water, will spontaneously self-assemble into membranes, forming little spheres or sheets, the basic structure of cell walls, emerging just from physics and chemistry.
Which brings us right to life itself. What is life, anyway? You mentioned earlier the source says there's no single, perfect, agreed-upon definition.
It's notoriously slippery to define precisely. The source mentions NASA's working definition, which they use when thinking about searching for extraterrestrial life, a self-sustaining chemical system capable of Darwinian evolution.
Self-sustaining.
Yeah.
Capable of evolution. That captures a lot about life on Earth.
It does. It highlights metabolism, self-sustaining chemical reactions, and genetics reproduction, evolution. But it might not capture everything we intuitively mean by life. Maybe it misses the feeling of being alive, or maybe future artificial life wouldn't fit neatly. Erwin Schrödinger, the quantum physicist, had a more poetic take. He thought of life as something remarkable that straddles stasis and change, maintaining its complex structure against the tide of decay while constantly engaging in dynamic processes.
From a purely physics and chemistry perspective, though, the source seems to say life isn't some extra magical ingredient added to matter. It's fundamentally a process, right? Something that happens when atoms and molecules are arranged in a particularly complex and dynamic way.
Exactly. It's about the arrangement and the process, not some mysterious life force or élan vital. Those were older ideas, vitalism, that science moved beyond as we understood more about chemistry and physics. It's like how we stopped believing in phlogiston to explain fire once we understood oxidation, or caloric fluid to explain heat once we understood it as molecular motion. Life is seen as an incredibly complex physical and chemical process.
And a key ingredient, maybe the key ingredient for this process, seems to be energy, specifically useful low-entropy energy.
Yes, what's often called free energy. Life absolutely needs a constant flow of usable energy from its environment to maintain its order and drive its processes. For plants, that's primarily sunlight. For animals, it's the chemical energy stored in the food they eat.
And life is basically a system for processing this energy.
In a sense, yes. It captures this free energy, uses it to do useful work like building complex molecules, moving muscles, replicating DNA, and in doing so, it inevitably degrades the energy into disordered waste heat, increasing entropy overall. Think of the ATP molecule in our cells.
The energy currency.
Right. It's like a tiny rechargeable battery. Chemical reactions charge it up into a high energy state, and then other processes spend that energy by breaking ATP down, releasing the energy to do work, and always producing some waste heat in the process. The source suggests life itself can be seen as a complex, evolving mechanism for releasing free energy stored in environmental gradients.
Okay, so life is this incredibly complex, open system that uses energy flow to maintain order and reproduce, driving evolution. But how did that whole process get started from non-living matter in the first place? Abiogenesis. That still sounds like the really hard part.
It is definitely one of the biggest remaining mysteries in science. We don't know the exact sequence of events, the precise chemical steps that led from simple molecules on the early Earth to the first self-replicating, metabolizing systems we would call life.
But the source emphasizes this is a scientific problem, right? Not something that requires invoking the supernatural.
Absolutely. It's seen as a problem within chemistry and physics, albeit a very difficult one. We understand the basic components that would have been needed. You need some way to store and replicate information. Maybe something like RNA, which can both store genetic info and catalyze reactions, came before DNA. That's the RNA world hypothesis.
Information storage. What else?
And you need metabolism, a way to capture and use energy from the environment to drive reactions. You need to harness energy gradients.
And the source mentions places like deep-sea hydrothermal vents as promising candidates for where this might have happened.
Yes, environments like the Lost City hydrothermal field are fascinating. They have alkaline water reacting with seawater, creating natural gradients in temperature, pH, and chemical concentrations. Lots of free energy available, along with mineral surfaces that could catalyze reactions and form compartments. It's a plausible setting for the emergence of early metabolic pathways.
So maybe metabolism came first.
That's one view. The famous quote from the biochemist Albert Szent-Györgyi, "Life is nothing but an electron looking for a place to rest," kind of captures this metabolism-first perspective life as fundamentally about harnessing energy flow.
But just reproducing isn't enough to be life, is it? The source uses the example of fire. Fire reproduces, it spreads.
Exactly. Fire makes more fire using fuel and oxygen. But fire doesn't pass on information about how to be fire in a way that allows for variation and selection for evolution. Life needs heredity information transfer from parent to offspring so that traits can be passed on and potentially modified over generations.
Like crystals, do they count?
Crystals are a simpler example of information transfer during reproduction. When a crystal grows or breaks, the new parts inherit the specific lattice structure, the arrangement of atoms, from the original. It's a form of information replication, but much simpler than life's genetic system.
Okay. So abiogenesis is the incredibly complex, still mysterious leap from non-living chemistry to that initial self-replicating, metabolizing system with heredity. And then evolution takes over.
Evolution is the engine that drives everything from those hypothetical, simple beginnings to the absolutely mind-boggling diversity and complexity of life we see today, from bacteria to blue whales to us.
And evolution itself is simply change over time.
At its core, biological evolution is just the change in the genetic information, like the frequency of different gene versions within a population over generations. Natural selection is one of the main mechanisms, probably the most important one for adaptation that drives this change.
So natural selection is the process where organisms with traits that make them better suited to their current environment tend to survive and reproduce more successfully.
And therefore pass those advantageous traits onto their offspring more often than organisms with less suitable traits. Over time, this leads to populations becoming better adapted to their environments.
So Darwin's big idea of natural selection, combined later with Mendel's work understanding genetics and how traits are actually inherited, that gives us the modern understanding of evolution.
That's the modern synthesis, yeah. And it's not just a historical theory. We can actually observe evolution happening, both in nature and in the lab. The source mentions the incredible long-term evolution experiment run by Richard Lenski.
What did they do?
They've been growing populations of E. coli bacteria in flasks since 1988. That's over 75,000 generations now. They freeze samples regularly, so they have a living fossil record. They've seen the bacteria get better and better at growing in their simple sugar medium, and they've even observed really interesting complex adaptations evolving, like the ability for one lineage to start metabolizing citrate, a chemical that E. coli normally can't use when oxygen is present.
And they could trace the genetic changes that allowed that.
Yes, they found it required several mutations to happen in sequence, a stepping stone process demonstrating how evolution can build complex traits incrementally over time.
So the key takeaway here is that evolution, driven by mechanisms like natural selection acting on random variation, is an unsupervised, impersonal process. It doesn't have a goal. It's not striving towards greater complexity or intelligence or consciousness or anything like that.
That's a critical point from the naturalistic perspective presented in the source. There's no built-in direction or purpose guiding evolution. Life is just this incredibly complex system, constantly adapting and changing, driven by feedback loops between genes and environments, powered by the flow of free energy.
And this incredible biological complexity isn't just external. It eventually leads to the emergence of an inner world. Thinking, consciousness.
Exactly. Which brings us to section 3, the inner universe, thinking, and consciousness. How do we get from electrochemical signals zipping around in a brain to subjective experience?
Well, the starting point seems clear enough. The scientific consensus is pretty solid. Thinking, feeling, experiencing, it's all intimately related to what happens in the physical brain.
Absolutely. Physically, the brain is this astonishingly complex network of nerve cells, neurons, connected to each other by synapses.
And billions of neurons, trillions of connections. The numbers are just mind-boggling.
They really are. And the source highlights something crucial. The information processing, the thinking, isn't just located in the individual neurons themselves. It's fundamentally about how they are connected and how they interact, the patterns of electrical and chemical activity flowing through this vast network. Mapping this network, the connectome, is one of the grand challenges of modern neuroscience.
Okay, so complex network, complex activity patterns. But this is where the really deep puzzle arises, isn't it? How does all that physical stuff, neurons firing, neurotransmitters crossing synapses, patterns forming and dissolving, how does that give rise to subjective inner experience? What it feels like from the inside to see the color red, or to feel the pang of regret, or just to be you experiencing the world right now?
That's it. That's the famous hard problem of consciousness, often associated with the philosopher Thomas Nagel and his question, what is it like to be a bat? How does objective physical brain activity generate subjective what-it's-likeness, sometimes called qualia?
Historically, people tried to solve this by separating mind and body, right? Dualism.
Yes, René Descartes is the most famous proponent of mind-body dualism. He proposed a fundamental separation between the physical stuff of the body and brain, what he called res extensa, extended substance, and the non-physical stuff of the mind or soul, res cogitans, thinking substance.
But that immediately raises a huge problem, which even his contemporaries pointed out. Like Princess Elizabeth of Bohemia asking him, if the mind is non-physical, how can it possibly interact with the physical brain? How can an immaterial thought cause your physical arm to move? Where's the point of contact?
Precisely. How does the ghost interact with the machine? Descartes famously, and rather unsatisfyingly, speculated about the tiny pineal gland in the center of the brain as the point of interaction, but that idea didn't really solve the problem and isn't taken seriously now.
And for modern physics, this interaction problem is even worse, isn't it? Because of the core theory we talked about.
Exactly. The core theory describes the physics of everyday life as a closed, rigid system. Particles interact according to precise mathematical laws. There's no room in those equations for some non-physical mind stuff to just reach in and push particles around in the brain without violating fundamental principles like conservation of energy and momentum.
So if an immaterial soul were influencing our thoughts or decisions by affecting neurons, it would have to be doing so in a way that changes the physical behavior of matter.
Which means it would have to be interacting via some force or mechanism that is itself part of the physical world and detectable by physics. If it's interacting, it's physical. If it's truly non-physical, it can't interact. So believing in an interacting non-physical soul essentially requires believing that our incredibly successful core theory of physics is profoundly wrong or incomplete at a very fundamental level, even for describing brains.
Okay, so if dualism has these major problems, what's the alternative from the perspective of poetic naturalism?
The naturalist or physicalist view is that thinking, feeling, consciousness, inner experiences, these aren't names for some separate substance or non-physical realm. They are instead ways of talking about incredibly complex physical processes happening within the brain. They are emergent phenomena arising from the intricate dance of neurons.
So mind is what the brain does.
That's a common way to put it. It's a description of the functioning, the processing, the patterns of activity within that physical system. But this view isn't without its own challenges, often brought out by philosophical thought experiments.
Like philosophical zombies. Always sounds dramatic.
It does. The idea is, could you imagine a being that is physically identical to a conscious person in every single way? Same atoms, same brain structure, same neuronal firing patterns, says the same things, behaves identically, but it has no inner experience, no subjective awareness. It's just dark inside.
Like a perfect automaton.
Exactly. If such a zombie is logically possible, the argument goes, then consciousness must be something extra, something non-physical that gets added to the physical setup, because you could have the physics without the consciousness.
And the physicalist response.
The physicalist response, as presented in the source, is basically to say, no, such zombies are not possible if physics, specifically the core theory as applied to brains, is a complete description of the relevant factors. If consciousness is just a way of talking about certain complex physical brain states and processes, then having that exact physical state means having the associated consciousness. Being physically identical at that level of complexity entails being conscious. The zombie scenario is conceptually incoherent if physicalism is true.
Okay. What about the other famous one, the Chinese room argument from John Searle? The person following rules to manipulate symbols without understanding.
Right. Imagine someone locked in a room who doesn't understand Chinese at all. They receive slips of paper with Chinese characters, questions, and they have a huge book of rules written in English that tells them exactly which other Chinese characters to write down and send back out, answers. By following the rules perfectly, they could fool someone outside into thinking there's a fluent Chinese speaker inside the room.
But the person inside still doesn't understand a word of Chinese. They were just shuffling symbols according to rules.
Exactly. Searle argued this is analogous to what computers do when they process language. They manipulate symbols according to programmed rules, syntax, but they don't have genuine understanding or consciousness, semantics. Therefore, computation alone can't create understanding or minds.
And the naturalist-physicalist response to that one?
There are several, but a common one, mentioned in relation to the source's perspective, is to question where the understanding resides. Maybe the person inside the room doesn't understand Chinese, but the entire system, the person plus the rulebook plus the room, does understand Chinese in a functional sense. Understanding in this view isn't some extra magical property. It's about having the right kind of complex, dynamic input-output relationships and internal processing. It's defined by what the system does and how it relates to the world, not by some ineffable inner quality divorced from function.
So from this naturalistic viewpoint, consciousness isn't a separate thing, but rather an emergent property. Like maybe something that arises when a system reaches a certain level of complexity, like water becoming fluid when you heat ice, a kind of phase transition.
That's one way to think about it, yes. Consciousness isn't likely a single monolithic thing anyway. It's probably better understood as a collection of related phenomena and abilities. Self-awareness, attention, memory access, planning, sensory experience, qualia, emotional states, the ability to model others' minds, and so on. Some of these aspects, like memory or attention, are becoming increasingly well understood in terms of specific brain circuits and processes.
But what about the really subjective part, the qualia? The redness of red, the feeling of pain, how does the naturalist account for that?
From the naturalist perspective discussed in the source, talking about the redness of red is a useful, high-level way to describe a particular complex pattern of neural activity in our brains. This pattern reliably gets triggered by certain external stimuli, like photons of a specific wavelength hitting our retina. It's connected to various internal states, memories of red things, associated emotions, linguistic labels, and it leads to predictable behaviors like saying, "I see red," or stopping at a red light. What it feels like is that complex, information-rich brain state in action. It's not something separate from the physical process. It is the physical process, described from the first-person perspective.
The source also briefly touches on ideas linking consciousness to quantum mechanics, which seem popular in some circles. Is there anything to that?
Well, it's sometimes jokingly called the law of minimization of mystery. Consciousness is mysterious, quantum mechanics is mysterious. Maybe they're related.
Right. Let's mash the mysteries together.
Exactly. But the source indicates, and this is the mainstream scientific view, that there's currently no compelling evidence or strong theoretical reason to believe that the known laws of physics, the core theory, need to be fundamentally revised, or that specifically quantum effects play a unique essential role in consciousness beyond their role in basic chemistry and signaling.
So ideas like Roger Penrose's arguments, based on Gödel's theorem, suggesting human intuition goes beyond computation, or speculations about quantum coherence and microtubules inside neurons. These aren't widely accepted.
They are generally considered highly speculative and lack strong empirical support within neuroscience and physics. The prevailing view is that classical physics and chemistry, operating within the incredibly complex network of the brain, are likely sufficient to explain the emergence of thought and consciousness. We don't seem to need new physics for it.
But conscious brains certainly give us some remarkable abilities. The source highlights things like mental time travel.
Yes, the ability to reflect on our past experiences and, crucially, to imagine and plan for future possibilities. This is incredibly powerful. The source mentions the sad case of patient Casey, who suffered brain damage that wiped out his episodic memory, his ability to recall personal events from his past. Interestingly, this also destroyed his ability to imagine or plan for his own personal future. He seemed locked in the present, showing how tightly linked our concepts of past and future self are in the brain.
And the other key ability mentioned is theory of mind.
Right, the capacity to attribute mental states, beliefs, desires, intentions, knowledge to ourselves and to others, and to understand that others have minds with states that might be different from our own. This is absolutely crucial for navigating complex social interactions.
The source mentions a robot example, Leonardo.
Yes, experiments with a robot named Leonardo suggested it could develop a rudimentary theory of mind. For instance, if it saw an object put into box A and then saw an experimenter leave the room while the object was moved to box B, the robot might later look for the object in box B, but indicate, perhaps by looking towards box A, that it knew the returning experimenter would believe the object was still in box A. It could model the experimenter's false belief.
That's fascinating. It makes evolutionary sense that these abilities, being aware of ourselves across time, being able to model the minds of others, would be incredibly advantageous for survival and success, especially for highly social creatures like us.
Absolutely. They allow for cooperation, prediction of others' behavior, learning from the past, planning complex actions. The list goes on. So the naturalist conclusion here is that consciousness, with all its facets, including subjective experience and these advanced cognitive abilities, is real and incredibly important, but it's an emergent property of the physical brain. It's a powerful and useful way of talking about and experiencing the results of highly complex information processing carried out by biological machinery, which is ultimately just atoms obeying the laws of physics.
Okay. So we've traced the path from the fundamental particles and forces described by the core theory, through the emergence of complexity in non-living systems, and then life via evolution, and finally to the emergence of thinking and subjective consciousness within brains. That brings us to the really big, deeply human questions, meaning purpose, morality. Our final section.
Right. Facing an impersonal universe. And this is where things can feel challenging. Because if the universe operates according to impersonal laws, if it wasn't designed with us in mind, if from the perspective of fundamental physics we are, as the source rather bluntly puts it, just blobs of organized mud that arose through undirected processes, well, it can feel like any sense of purpose or meaning is just an illusion.
Yeah, it can feel like something profound is lost. If there's no inherent cosmic purpose for us, like why bother? does anything truly matter?
This is precisely where the source offers what it calls existential therapy. The argument is, okay, the universe is governed by impersonal laws. It didn't create us for a specific reason. We aren't the center of cosmic attention. However, that does not mean we don't matter or that meaning isn't real.
How does that work?
This isn't a scientific claim you can prove with data, obviously. It's a philosophical stance, a way of framing our existence. The argument is that the old way of thinking, the idea that if we're just atoms governed by physics, then we can't really be significant or have purpose, is based on a flawed premise. It's buying into the idea that the only valid way to talk about ourselves is the fundamental physics description.
Back to poetic naturalism. Being atoms isn't the only true story about us.
Exactly. We are collections of atoms obeying the core theory. Yes, that's one true story. But we are also simultaneously thinking, feeling, complex beings who live, love, suffer, strive, build relationships, create art, explore science. That's another equally valid, emergent way of talking about what we are. And it's at this level, the human level, that meaning and purpose arise.
So meaning isn't something we discover out there written into the fabric of the cosmos. It's something we create in here through our lives, our choices, our connections, our values.
That's the essence of the naturalistic perspective offered. Meaning is constructed, not discovered. And this connects directly to morality and values and a very important philosophical point raised by David Hume.
The Isought problem.
That's the one. Hume famously pointed out that you cannot logically derive an ought statement, a statement about what should be, a value judgment, purely from is statements. Statements about what is the case, factual descriptions. There's always a logical gap.
Just because something is a certain way in nature doesn't automatically mean it should be that way, or that it's good or bad.
Precisely. The source uses an example from the philosopher John Searle to illustrate how we often sneak oughts in. Saying the words, "I promise to pay you $5, is a factual statement about making sounds, but we immediately think it implies an ought. I ought to pay you the $5.
But how do we get from the is of speaking words to the ought of obligation?
Hume's point, and Carroll echoes it, is that there's always a hidden, often unstated bridging premise that contains the value judgment. In this case, it might be something like, one ought to fulfill valid obligations one voluntarily enters into, or promises made under appropriate conditions should be kept. That's the ought doing the work, and it wasn't derived from the factual statement alone.
And why does this matter? Because those hidden value premises are often the things people actually disagree about.
Exactly. That's where the real ethical arguments often lie. Science is incredibly powerful at figuring out what is. The universe is expanding. Humans and chimpanzees share a common ancestor. Burning fossil fuels changes the climate. These are factual claims, potentially falsifiable by evidence. But moral statements like, we should strive to reduce suffering, or protecting biodiversity is good, or individual liberty ought to be maximized. These are different. They aren't directly testable by scientific data. They depend on our goals, our values, our judgments about what kind of world we want to live in. Science can inform our moral decisions by telling us the likely consequences of our actions, but it doesn't dictate our ultimate goals or values.
Okay, so if values and oughts aren't objective facts written into the universe like the law of gravity, and science can't derive them for us,
Yeah.
where do they come from in this naturalistic framework? Are they just totally made up? Arbitrary?
They're constructed by us, yes, but not necessarily arbitrary. They gain their reality and their force from our shared human experience, our evolved psychology, our biology, our social interactions, and our collective reasoning about how to live together.
So our moral impulses have roots.
Definitely. They aren't pulled out of thin air. They're influenced by the structure of our brains. Psychologists like Joshua Green talk about a dual process morality, with fast, intuitive, often emotionally driven responses, sometimes linked to rule-based or deontological ethics, don't push the guy, competing with slower, more deliberative cognitive reasoning, often linked to consequentialist ethics, save the 5 people.
Like in the trolley problem thought experiments. Pulling a switch versus pushing someone off a bridge feels different, even if the outcome is the same.
Exactly. Those dilemmas highlight these conflicting impulses within us, and these impulses themselves have evolutionary roots. Work by primatologists like Frans de Waal shows precursors to human morality, empathy, fairness, cooperation, conflict resolution in our primate relatives. Our social nature has endowed us with a suite of pro-social instincts and emotions that form the raw material for our moral systems.
So our constructed morality isn't random. It's built upon this foundation of evolved social instincts and our capacity for reasoning about consequences and principles.
That's the idea. We build systems of ethics, whether focused more on duties and rights, deontology, or on outcomes and well-being, consequentialism, or on virtues, by reflecting on these intuitions, reasoning about their implications, and trying to find coherent ways to achieve our shared goals.
Which leads to what the Source calls the potentially terrifying conclusion for some people. That morality in the end isn't based on some external, objective, absolute standard given by God or the cosmos, but on our shared feelings, preferences, and goals, on what matters to us.
That is the naturalistic conclusion presented here, yes. And the immediate worry people often have is, well, if it's just based on what we want or feel, won't people just make up self-serving rules? Won't societies collapse into chaos or tyranny if there's no absolute anchor? This is a very old concern raised against naturalists and humanists for centuries.
But the response is that fear is overblown. Our shared nature guides us.
The response is that our construction of morality isn't happening in a vacuum. It's deeply constrained and guided by our shared human nature and the realities of living together on a planet. We generally do share fundamental desires and goals. We want to avoid suffering. We seek happiness and flourishing for ourselves and those we care about. We need cooperation and trust to build stable societies. We value fairness, mostly. These common grounds provide a powerful, non-arbitrary basis for building workable ethical systems and engaging in moral progress, even without appealing to anything supernatural or cosmic.
So, meaning, morality, purpose. They aren't part of the core theory of physics. They aren't out there in the atoms. But they are real and vitally important as emergent concepts at the human level. They matter because they matter to people.
Precisely. They gain their reality and significance from our conscious experience, our relationships, our shared values, the stories we tell ourselves about who we are and what we aspire to be. The Source offers something like 10 considerations, practical points of wisdom that seem to flow naturally from embracing this poetic naturalist worldview.
What sort of thing?
Things like genuinely accepting that life is temporary. The Source uses the striking idea of having about 3 billion heartbeats in a modern lifetime. Use them well. Recognizing that desire and striving are built into being alive. Embracing the fact that there's no single natural or correct way to live a fulfilling human life. Diversity is key. Letting reality be your guide. Update your beliefs based on evidence, even when it's uncomfortable. Acknowledging we can always do better. Learn from mistakes. Avoiding self-deception facing reality is ultimately better than comforting illusions. Remembering that what matters is what matters to people. Realizing the future is, to a large extent, in our hands, valuing different approaches to finding fulfillment, and crucially, listening to others and to the world.
It sounds like facing the reality of our situation in an impersonal universe. While maybe initially daunting, that existential therapy idea can ultimately be quite liberating and lead to a deeper appreciation for the life we actually have.
It really can. The Source suggests it's like humanity collectively growing up, moving away from comforting childhood stories about being the center of attention and taking responsibility for creating our own meaning. Understanding the sheer improbability and preciousness of our existence, as Carl Sagan and Ann Druyan so eloquently expressed, can make life feel more meaningful, not less. Their famous quote about finding each other in the vastness of space and the immensity of time captures that feeling the meaning comes from the connection itself, made all the more poignant by the cosmic context, precisely because it wasn't preordained.
So life, from this perspective, is this incredible, complex, emergent process of change and passage. And understanding the big picture, the underlying physics, the evolution of complexity, the nature of our own minds, doesn't drain the meaning out, but actually helps us appreciate the present moment more fully and think more clearly and responsibly about building the future we want.
That awareness gives us agency. It frees us from seeking purpose where it isn't found in the fundamental laws, and empowers us to find it where it truly resides in our own life, choices, and connections. We get to decide what we value and how we want to live, rather than hoping some external authority will tell us.
So, wow. We've really journeyed today, haven't we? From the fundamental particles and forces described by the core theory, weaving through the emergence of complexity in life via evolution fueled by entropy and free energy, exploring the mysteries of consciousness as an emergent property of brains, and finally confronting the profound human questions of meaning and morality within a naturalistic framework.
It's a huge landscape. But the core takeaway from the perspective in the big picture is, I think, quite clear and consistent. The universe itself operates according to impersonal, elegant, fundamental laws. It doesn't have us in mind. But Meaning, value, purpose, and even consciousness itself are not illusions because of that. They are real, critically important, emergent features of the world brought into existence by us by complex, conscious beings who think, feel, interact, and care. They matter profoundly because they matter to people.
And knowing this, knowing that life is this complex, temporary, emergent process, the source leaves us with a striking thought, reminding us that in a typical modern lifetime, we each get about 3 billion heartbeats. That's it. In a universe that doesn't assign you a purpose from the outside, what will you choose to do with yours?
How will you choose to bring meaning and value into your own fleeting existence and into the lives of others, understanding that, from this perspective, it is uniquely our creation, our responsibility, and our privilege? It's a powerful question to sit with, grounded in this vast, scientifically informed big picture we've explored today.